Welcome to Lesson 14. In this lesson, we are going to study how heat for a chemical change can be calculated. By the end of the lesson, you should be able to define specific heat capacity, calculate heat, mass, change in temperature, and specific heat capacity for a physical change, and describe how differences in mass and specific heat capacity will change how a substance warms or cools. We have already discussed how to calculate heat for a chemical reaction using reference table I, where a minus sign indicates an exothermic reaction where heat is lost, and a plus sign endothermic. Work on solving word problems. For each word problem or heat calculation, we are going to be using one of three formulas. These formulas are found on reference table T. Reference table T has to be used in conjunction with reference table B, as each equation has a constant found on reference table B. That constant is underlined here in red. It is either C, the specific heat capacity of water, H sub V, the heat of vaporization, or HF, the heat of fusion. Notice on the graph I've put where we're going to use these three constants. So when the temperature changes, we're going to use Q equals mc delta T. C, the specific heat capacity of water, is 4.18 joules per degree Kelvin. When the temperature is not changing at the plateaus where we have phase changes, we're going to use the heat of fusion, 334 joules per gram, or the heat of vaporization, 2,260 joules per gram. Notice the heat of vaporization is much larger than the heat of fusion. Therefore, it requires much more energy to break all intermolecular forces that hold a liquid together than it is to loosen the intermolecular forces between a solid and a liquid. Before we solve any heat equations, let's look at the factors that affect the change in temperature. The first factor is mass. If we try to heat up both of these beakers on the same hot plate or stove, obviously the beaker with less mass will change temperature faster than the beaker with more mass. Another important factor that influences how quickly something heats or cools is the intermolecular forces that are found in the substance. This important physical property can be seen in your kitchen. When heating up water and oil, one should note that oil will get hotter much faster than water, and you should use great caution when cooking with oil, as since it can get hotter than water, it can cause more severe burns than water. So make sure that you fill out your data table on your notes packet. Here we can see the Q equals mc delta T equation and what each variable stands for. Remember that the delta sign means change of. It typically measures the second temperature minus the first temperature. We will note to use these equations when the temperature is changing. We can see these keywords in a word problem when we need to apply this equation. Temperature change, temperature increased, temperature decreased, initial or starting temperature, final temperature, ending temperature, from and to, water, and we can also look for the words cools and heats or warms. So when we break these questions down to simpler steps, they're really easy to do. First off, delta T is the final temperature minus the initial temperature. So when we do this practice problem, and a calorimeter, or a device that measures changes in heat, contains a solution at 93 Celsius and it cools to 34. If we subtract 34, the final temperature, from 93, we'll get a negative number, indicating that heat is lost. So this corresponds with an exothermic reaction. In the next example, we are looking for the delta T when the temperature outside is -5 and the temperature inside is 32. If we take the final temperature minus the initial temperature, you'll see that we'll have a positive value. This positive value means that this temperature change corresponds with an endothermic reaction where heat is added. Let's do some more practice problems. In this practice problem, we are calculating the amount of heat in joules 32 grams of liquid water absorb when it is heated from 25 degrees Celsius to 80 degrees Celsius. The first thing that you must always do is set up a variable table. So here we're looking for Q, which is heat. So we can assign this the variable X. We are given the mass and the change in temperature. Remember, one value is always coming from reference table B. That is the specific heat capacity. Once we substitute, all we have to do is use our calculator to solve. Notice that this is an endothermic reaction as represented by its positive delta H. In this example, a lump of silver has a heat capacity of 42 joules and a mass of 181 grams. The change in temperature is 25. The first thing you must do is set up a variable table. We are given heat, mass, and the change in temperature. Because we are not dealing with water, we cannot use this heat capacity of 4.18. We substitute and solve. Notice that silver has a very small heat capacity, meaning it quickly heats up and quickly cools down compared to water. Here is another question where we're given 132 joules of energy to heat 11.17 grams of aluminum, whose specific heat capacity is given. If the original sample reached 75 degrees Celsius, what is the original temperature? So the first thing we'll have to do is set up a variable table. It is easiest if we have delta T be our X. Remember, we cannot use 4.18 because this is not water, this is aluminum. Each sample has a unique specific heat capacity. Now we're ready to substitute. It is important to remember that delta T is not the same thing as original temperature. We'll get to that at the end. So first we'll substitute and then we'll solve. Now our answer now tells us the change in temperature, but we are not looking for the change in temperature. We are looking for the original temperature. So we'll have to use this value in conjunction with the final temperature to find the original temperature. When we solve this algebraic equation, we will be left with our final temperature.
That was our original starting temperature that the aluminum was at before it was heated.
When applying Q equals mc delta T, we have the variable C, or specific heat capacity. It is officially defined as the amount of heat necessary to raise the temperature of 1 gram of a substance 1 degree Celsius. The specific heat capacity of water is 4.18. It is very large compared to many other substances. That's why water takes a really long time to heat up. Substances with a high specific heat capacity have large heat banks, so they take a long time to heat up, but they also take a long time to cool down. That's why cities near large bodies of water have more temperate climates. That's also why cities that don't have water nearby, like deserts, tend to have large fluctuations in temperature. Sand has a very low specific heat capacity, so it heats up very quickly. It also cools down very quickly. Try and think about pizza. A lot of times you can grab the slice of pizza and hold the crust in your hand, but the cheese burns your mouth. Do you think cheese has a high or low specific heat capacity? Does it have a large heat bank and take a long time to heat up and a long time to cool down? Or does it have a small heat bank, so it heats up very quickly and also cools down very quickly? Specific heat capacity measures how quickly a substance heats up or cools down. A substance with a small specific heat capacity, like the liquid metal mercury, heats up and cools down very quickly, while a substance with a much larger specific heat capacity that you can see here, like that of water, will heat up and cool down very slowly. This is the end of the video of lesson 14. Bring any questions you have to class. I can't wait to go over them.